In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. Chart a daring course with comets, the cosmic time travelers of the skies.
These mysterious objects have been agents of change. They've been agents of destruction.
Discover why these celestial bodies carry secrets from our past and cast doom over our future.
If it's getting into our on-ramp, we need to worry about it.
There's very little we can do other than sending a giant bomb toward them and trying to deflect them.
Brace yourself as we rendezvous with the frozen intruders from the great beyond on an epic journey to ride the comet. They appear out of nowhere, gliding slowly across the nighttime sky, and then disappearing from sight. Throughout human history, ancient cultures believed these celestial intruders carried special powers from the gods, mystical messengers of life and death.
Scientists like to think that comets are fairly mysterious objects because we know that they're very old. They're like frozen time capsules from when our solar system was first formed.
Comets are a bit of show-offs. They come into the night sky unannounced, unpredicted. In the Middle Ages, they were thought to be fireballs thrown at a sinful Earth from the right hand of an avenging god. And so they've always been feared or seen as mysterious.
We're going to hitch a ride on a bold, uncharted journey through the secret life of our solar system's comets. Our daring quest begins 4.5 billion years ago as our futuristic spacecraft time travels back to the birth of our solar system. We zigzag through a maelstrom of debris to catch our first glimpse of comets, the wayward rocks that didn't meld into planets.
Comets are basically dirty snowballs or icy dirt balls. They consist of rocks and dust and dirt held together by ices, water ice, ammonia, methane, carbon dioxide, dry ice. That's sort of like the glue that holds all these little pebbles and particles of dust together.
The heart of these cosmic icebergs is the nucleus, or central core, which averages in size from a half-mile wide to as big as a modern city.
One of the things we've learned by flying close by and observing the nuclei of comets is that they're these strange sort of compacted conglomerates of ice and rock. They're not uniform, they're not perfectly mixed, they're quite chunky and oddly shaped.
The nuclei of comets are very fragile entities. If you had a chunk, you could probably break it easily in your hands.
Up close, comets look like bland chunks of charcoal rather than supersized snowballs. They don't even remotely resemble the glowing orbs we see in our pitch-black skies.
We think that most comets are extremely dark on their surfaces, that the surfaces are covered with something kind of like barbecue soot, this really dark black material that makes them very difficult to see.
While their asteroid cousins share similar properties, such as rock and metal, scientists suspect that comets were born farther out, near the gas giant planets, where it's much colder. So they possess more ices and volatile elements. About 3.8 billion years ago, many of these icy bodies were whisked away to the Kuiper Belt, a frigid neighborhood just beyond the outermost planet Neptune.
Icy objects in the Kuiper Belt probably formed closer in toward the sun, where the giant planets are. But then gravitational interactions with those giant planets made those icy objects migrate outward.
Our spacecraft navigates through this dark, disk-like region, which is almost 2 billion miles wide and is estimated to hold over 6 billion comets. We eventually touch down on the surface of one of these icy boulders.
Landing on a comet would be a pretty tricky affair. So you could kind of imagine dirty snow that's covered with exhaust. And if you step on it in places, you can punch through to places where there's more fresh material underneath it.
The Kuiper Belt objects appear to have fairly stable orbits, so they won't be that much fun to ride. We lift off in search of a comet that will cut a more exciting path through our solar system. We navigate farther out to a sparsely populated region called the scattered disk, which is home to icy bodies with long elliptical orbits. The slightest disturbance can send these unstable objects careening into the inner solar system, where they become known as short-period comets, those which orbit the sun every 20 to 200 years.
The scattered disk region is thought to be the primary source of the short-period comets. They are kicked into the inner solar system either by interacting with Neptune or possibly passing the stars.
Our spacecraft witnesses Neptune's gravitational influence at work, dislodging a comet out of the scattered disk. This comet would be too dangerous to land on, so we'll track alongside it on its transformational flight through our solar system.
So what would happen if it was on a journey toward the sun? Well, it would start off looking like a dark asteroid. Nothing much is happening. It doesn't have an atmosphere around it.
As you start to travel toward the inner solar system, get up to Jupiter or even closer to the sun, the comet would start to become active.
The warmth from the sun starts to heat up the comet, and all the frozen material that's trapped on the inside starts to convert from ice into gaseous material. And so these gas jets can actually punch through the crust of the comet and form jets. As these jets flow away from the surface, they can start to pull dust and rocks with them. And this forms a kind of hazy atmosphere around the comet's nucleus. We call this the coma.
As it zooms by Earth, the coma of a comet can grow to be larger than the diameter of our sun. Solar radiation eventually pushes this cosmic halo behind the nucleus, forming two bright tails, one of dust and the other of gas.
So there'd be a tail growing and growing and growing, and you would eventually become engulfed in just a really rocky, icy, particle-filled environment. It would be very difficult on your spacecraft because it'd be like flying through a blizzard.
Some tails can stretch for 100 million miles, more than the distance between the sun and the Earth, as it travels towards our home star. It's one of the most spectacular spectacles of our solar system.
Today we're going to see what happens when we take a comet that's been in the cold, dark, icy outer reaches of the solar system, and we're going to send it inward towards its perihelion, or the point of closest approach to the sun. Now, dry ice is frozen carbon dioxide, and this is a very common constituent of comets. Let's see what happens. When we take this piece of dry ice and we drop it into the warm water, the dry ice starts to sublimate. That means it converts directly from a solid frozen state into a gaseous state. And as the water starts to warm up certain parts of the dry ice first, you can start to see that little jets kind of form on it. And this forms a hazy atmosphere called a coma. You can see that the little chips of dry ice are constantly changing as they sublimate away. Sometimes they speed up, sometimes they slow down. So if this was a comet, you can get the idea that as the comet approaches the sun and the volatiles start to vaporize, this can actually change the comet's rotational state and even its orbit.
Comets are brightest and fastest when they're closest to the sun. The searing heat and immense gravity of our mother star can accelerate a comet's speed to nearly 2 million miles per hour.
the speed increases a lot and it whips around the sun. So it goes zoom like that, like being propelled at the bottom of a giant roller coaster. A roller coaster starts out high very slowly, picks up speed due to gravity, goes zooming past the bottom, and then slows down again on its outward journey.
Eventually, as our comet leaves the vicinity of the sun, it's going to travel back out into the far reaches of the solar system. Everything's going to quiet down. All the gas and dust is going to settle back onto its surface, and eventually it'll cruise away into the quiet dark.
Back in the cold region of the scattered disk, a comet transforms back into a dull black lump of rock and ice until it makes its journey around the sun once again. Halley, the most famous short-period comet, was first recorded in 240 BC and has passed by Earth every 76 years. Estimated to be the size of Manhattan, this superstar comet is sometimes so bright it has been seen in broad daylight. Throughout history, the appearance of Halley has inspired awe and dread among earthly observers.
In 1910, it was feared because spectroscopy had just been introduced and they had determined that comets contain cyanogen, which is an odorless and poisonous gas, and so astronomers predicted that there'd be problems because of this poisonous gas sweeping the Earth, and so there were actually comet pills manufactured. Life insurance policies on the comet were taken out.
While comets have been thought to be extraterrestrial harbingers of doom, astronomers have long wondered if these glowing rocks contain precious information about our past. By the 21st century, NASA was ready to ignite a bold offensive strike, one that would hopefully expose one of the holy grails of planetary science. Could these interplanetary vagabonds have been the cosmic transporters of life? So far, we've traveled with comets, from the frozen hinterlands of the Kuiper Belt and scattered disk to an exhilarating orbit around the sun. We've watched these dark bodies come alive as they formed brilliant comas and tails. But scientists are still puzzled about what's really inside these cosmic interlopers.
Man, I wish I knew what the interior of a comet looked like. You would love to be able to look inside the nucleus of a comet to see if it's clumpy, if it's uniform. Is there crystalline ice? Is there glassy ice?
Our protective spacecraft time travels back to 2005 and meets up with NASA's Deep Impact Space Probe on a comet hunting mission. It zeroes in on a short-period comet named Tempel 1 with an aggressive plan of attack. We hover at a safe distance as Deep Impact launches an 800-pound projectile into the passing comet. Debris sprays out for thousands of miles as the impactor excavates a crater and sends tons of blinding gas, rocks, and dust into space. For the first time in history, scientists are able to peer inside the icy, muddy interior of a comet.
Right after the impact, you could see silicate grains fluorescing and glowing. This tells us that comets are very primitive material and that they pretty much do preserve in pristine state the materials that we find in the youngest star-forming systems. So indeed, they really are time capsules that let us look back on our own solar system at the very beginning.
While Deep Impact captures a rare glimpse of a comet's interior, it is unable to snap clear images of the crater, which was obscured by an enormous plume of debris. In February 2011, another spacecraft named Stardust Next catches up to Tempel 1 as it completes its 5-year orbit around the sun. To everyone's surprise, the impact crater is much smaller than had been expected from the historic smash-up that occurred 5 years earlier.
Amazing. But the crater looked like it was small. So this now creates this issue. Was the crater always small? We know the crater isn't what we expected. So we're going to do some experiments to see if we can explain why the crater looks like it does.
So lamp's coming on.
Can you move up a bit?
At NASA's Ames Vertical Gun Range, Stardust Next co-investigator Pete Schultz is conducting high-velocity impact experiments to find out why deep impact produced such a tiny crater. He will use a massive 30-caliber high-velocity gas gun to fire tiny projectile beads at various targets located inside a vacuum chamber.
We're trying to simulate what the nature of the surface of Comet 9P Tempo 1 is like. So we're putting in perlite, which is this low-density material that you find in gardens, and we're adding in hollow microspheres. And this also resembles what the nature of the comet is like. So the purpose of the experiment is to see what happens to the crater after formation. Does it stay there? Does it collapse? With this experiment, we should be able to find out. Okay, I'm out of the tank. Lock and load.
High-speed cameras mounted around the vacuum chamber will document the impact.
We've got this one covered. We just have to hit the target. Okay. Let's shoot this puppy. JP, are you ready?
As the crew anxiously awaits in the control room, Pete mixes science with a little superstition.
It's always a risk. Sometimes we miss, sometimes we hit. Whoa. Oh, sweet. The whole thing sort of collapses in on itself. It's getting smaller now. It was bigger, now it's getting smaller. So what we see here is that there's a lot of dust and ejecta sent upwards, and that blocked the view. We couldn't see the crater forming. So what started off being a nice-looking crater, it just doesn't stay there. It just simply heals itself. So what may have happened for 9P Tempo 1, the nucleus, is that the crater healed itself. The nucleus healed itself from the scar created by us with deep impact. Let's see what we did. So the results were fantastic. We got to see just what we planned to. There may be more to the story, so we're going to try a different experiment as well.
Pete has a hunch there's a missing piece to the deep impact mission. He now wants to see if the space probe created a different type of crater on Tempo 1 due to the makeup of the comet's nucleus.
So this time, we're going to put a denser layer below that perlite. So we want to find out whether or not we'll get a different type of crater if we have two different types of material, one very soft on top and one denser on the bottom.
Pete and his crew return to the control room to see what happens to the new target of perlite poured over a heavier layer of sand.
Oh! Now that formed a big crater in the perlite. Boy, look at that. Oh man, that is gorgeous. Okay. The projectile went deep, and now the stuff is coming back out that hole, while on the surface, it's excavating debris. Pow, okay.
The double-layered target created not one, but two craters. A small crater inside a larger, shallower crater.
This could be what happened for 9P Tempo 1. It went so deep into the nucleus. And then it just simply collapses away, and we're left with just this very, very faint rim on the outside with a small pit in the center.
These impact experiments yield surprising clues about the interior of Tempo 1, and perhaps all comets.
Now we know that comets have history. We see layers. I don't know if these layers go all the way through the nucleus, or are they only in one part?
Unraveling the secrets of what's inside comets will help scientists understand what causes them to exhibit some really bizarre behavior. Our spaceship now shadows NASA's epoxy mission as it encounters Hartley 2, a fast-spinning comet that tumbles through space like a hyperactive cosmic peanut.
Hartley 2 is a smaller comet. It's only about a mile or so across, and so it's kind of a surprise that it's so active. It's putting off huge amounts of CO2 and actually cyanide gas. And the question is, are all small comets active like this, or only a few? And what makes them so active? I've got a peanut-shaped plastic bottle here that's supposed to represent Comet Hartley 2. It's full of dry ice and warm water, and as you can see, as the warm water starts to make dry ice sublimate, it shoots out these jets through the holes that we've got poked in the bottle. If I drop it into the water, instead of holding it fixed in space, and you can see that the jets actually start pushing the bottle around, causing the comet's rotational state to change. This is very similar to what's going on the surface of Comet Hartley 2. The CO2 jets are actually changing the rotational state of the comet, causing it to speed up and slow down.
When tracking Hartley 2, our spacecraft gets caught in a cosmic blizzard as the spastic comet burps and belches out a trail of frozen snowballs that extend for millions of miles.
One of the big surprises about Hartley 2 is that it was surrounded by this posse of mini comets. This is simply ices that are coming off about the size of a snowball all the way up to a basketball.
Scientists suspect the snowball-sized debris rains back down on Hartley 2, producing its unusual landscape of craters and towering spires.
Because these comets have very little gravity, most of the gas is blown out into space, but a very small fraction can actually redeposit on the surface, generating very smooth textures, and in other locations, generating this very bumpy or spired-like texture.
From Hartley 2, we blast off to the extreme outer edge of our solar system. A vast, eerie place, barely within the gravitational grasp of our sun, and impossible to see even with modern telescopes. Here, we come upon the largest and perhaps most elusive icy bodies in our galactic neighborhood. Our journey through the fascinating world of comets has provided us a ringside seat to some of the greatest cosmic shows observed from Earth and space. We now change course and travel over 50,000 times the distance between Earth and the Sun to the outermost edge of our solar system. We arrive at the Oort cloud, an even larger fraternity of comets, perhaps over 1 trillion of them.
If we'd actually gotten a spaceship and tried to go out and, say, visit the Oort cloud, this would have been a long journey. There's billions and billions of these objects, but there's a lot of space in between them.
Like the Kuiper Belt and scattered disk, the Oort cloud objects may have formed closer to the Sun. But about 800 million years after the solar system was formed, the gravitational influence of the gas giant planets flung these comets out to the frigid edge of our solar system.
Some of these objects were flung into very highly elliptical orbits out into the Oort cloud. Passing stars could circularize those orbits, making somewhat stable orbits for them.
Most of the Oort cloud bodies have been in frozen hibernation since the birth of our solar system. They only become long-period comets when they get sucked into orbits that carry them inward towards the planets and the Sun. Scientists have never actually captured an image of the Oort cloud, but they have good reason to believe it's there.
Even though scientists can't directly observe the Oort cloud because it's so far away and so faint, what they are able to do is infer its existence because we can look at where all these long-period comets come from on the sky. and they seem to come from all different directions. There doesn't really seem to be a preferred direction for them. This suggests that the Oort cloud, if it exists, is probably roughly spherical.
One of the big mysteries is what knocks these icy bodies off course and sends them cruising by our neighborhood of Earth.
The comets in the Oort cloud are very susceptible to gravitational pulls from other things outside the solar system. One thing is passing stars. If a star happens to come close to our sun, it can scatter comets from the outer Oort cloud.
Icy objects in the Oort cloud can also be dislodged by gravitational perturbations that occur when the solar system goes through the plane of our galaxy. So the solar system is basically orbiting around the center of our galaxy, but it's also oscillating up and down. And when it goes through the plane, then gravitational interactions can perturb objects from the Oort cloud into the inner solar system.
Some long-period comets take up to about 30 million years to complete one round trip around the sun. Our spacecraft tracks a long-period comet for hundreds of thousands of miles until we approach planet Earth. As its icy tails unfurl, a layer of dust and ice zips through our planet's thin atmosphere, leaving visible trails known as a meteor shower.
I like to think of comets as sort of the pig pens of the solar system, because as they orbit around the sun, they leave a big messy trail of debris. But sometimes the Earth's orbit can intersect some of these dust bands, and when it does, we can sometimes see meteor showers. And those beautiful bright streaks of light that you see coming through the night sky are actually produced by particles that are most often no bigger than a sand grain.
While long and short period comets make up the bulk of comets that have been observed, new evidence suggests that not all icy bodies come from the sub-zero suburbs of our solar system. Some have secretly taken up residence in a much warmer neighborhood. Scientists have now discovered there are comets masquerading as asteroids in the asteroid belt, located between Jupiter and Mars.
The only reason that we've discovered these main belt comets is because occasionally the warming rays of the sun get into the interior, vaporize the ices, and so the comet just bursts forth for a while, and then they go back to being inactive objects or asteroids.
Scientists used to think that there were strong distinctions between asteroids and comets, and that there were two totally different types of objects. But what we're finding nowadays is there are some asteroids that have comet-like properties, and there are some comets that eventually kind of look like asteroids.
Some scientists think main belt comets may have delivered water to early Earth and the materials to create life. We blast back to January 2004 and follow NASA's Stardust spacecraft on an unprecedented mission to collect pure comet dust in space. Just beyond the planet Mars, we meet up with a comet named Wild 2. Upon approaching its enormous coma, Stardust flips open a paddle-shaped collector tray filled with a durable foam-like substance called aerogel. Cometary particles no bigger than specks of dust fly into the aerogel at 6 times the speed of a rifle bullet. The mission's task is to preserve the precious particles without damaging or altering them. But this is no easy feat, as we show here on Earth.
We're here at a firing range with Sergeant Connet Brewer, a former Army paratrooper, who's going to demonstrate for us what happens when this birdshot strikes a large block of modeling clay. This is an excellent analogy for what happened when cometary particles impacted the aerogel on the Stardust spacecraft, except there, the particles were moving about 50 times faster than this birdshot. Ready to give it a go?
Yes, I am. Go ahead and put on your eye protection and your earplugs. What we're using for this today is a 12-gauge Model 1100 Remington shotgun at a distance of about 35 yards. Basically, I'm just going to load a 12-gauge shot shell into the shotgun, And we're hot.
Whoa! It really did some damage to that clay. Do you want to go take a look?
Yeah, we're clear.
All right. Wow, look at the damage it did to the clay.
Yeah.
So each pellet created one of these holes. So what do you say we cut this open and try to find some pieces?
Sounds good.
All right. So you see the trail here that's formed inside the clay is going to lead you ultimately to where the birdshot pellets are located. You can imagine how difficult it would have been and how time-consuming for the Stardust team to locate these microscopic pieces of cometary material inside the aerogel.
Upon Stardust's return to Earth, scientists recovered over 10,000 cometary fragments from the aerogel. Chemical analysis revealed that the particles contained the organic compound glycine, a fundamental building block of life that had been preserved in ice for over 4 billion years.
The discovery of organic compounds in comets suggests that organic compounds can form pretty easily. Now, it doesn't mean that there was ever anything truly alive in those comets, but at least the building blocks of life could have been built in comets.
Comets appear to hold invaluable information about the origin of our solar system, and perhaps life itself. But astronomers have discovered that these icy bodies are not immortal. Now, state-of-the-art satellites have captured images of a select group of comets that will end their life in a suicidal death dive. While our journey with the comets has felt like an endless cosmic roller coaster ride, these icy objects will not orbit our sun forever. Most will make the voyage for several thousand years before evaporating into specks of dust. Even massive comets, like Halley, only have 150,000 years left. That's because every second, a comet loses tons of ice.
Comets gradually wither away or fade away because every time they pass close to the sun, they lose some of their ices. They evaporate away. Eventually, there's very little ice left, and so the comet coma and tail doesn't form. It just looks like an asteroid. Or it may even break apart into a whole bunch of little objects because the icy glue is no longer there, or because tidal effects actually break it apart.
But not all comets quietly fade into the sunset. We're now in hot pursuit of a group of comets called sun grazers that live fast and die young. Inside our spacecraft, we feel the heat as the comet's extremely elongated orbits bring us very close to the sun, within a few 100,000 miles. As we enter this danger zone, we see that some of these kamikaze comets occasionally plunge right into our home star, creating a ferocious spectacle.
Sungrazer comets start out their life as normal comets. They probably live either in the Oort cloud or they're short-period comets, but they've had an unlucky encounter with another planet, probably Jupiter. If they're really, really lucky, they might just escape and be able to get away with one close passage by the sun. But if they're not lucky, they just get swallowed up whole by the sun.
The Solar and Heliospheric Observatory, or SOHO, is a space satellite that has observed 2,000 comets on suicidal orbits. The most famous sun grazers are the Kreutz family, which originated from one giant comet that broke up into many smaller pieces.
It's a kind of cool thing to think of a comet that's lived in the outer solar system just falling all the way and smashing into the sun. But they do, we see them all the time.
And some comets do more than self-destruct. they become the messengers of mass destruction. It's estimated that a large comet may have struck Earth roughly every 40 million years, based on the amount of craters still visible on our planet. A comet may have even been responsible for the most famous extinction event of all time.
For the Cretaceous Tertiary extinction event, the one that took out the dinosaurs 65 million years ago, the jury is still out. That was thought to be a 10-kilometer sized object, and there are no asteroids in near-Earth space that are that large that could impact the Earth. And there are a number of comets that are that large. And since it occurred 65 million years ago, and you would expect a cometary impact every 40 million years or so, it may well have been a comet.
While comets most likely slammed into Earth countless times in the past, it's been difficult to determine if an impact crater was made by a comet or asteroid, because the two bodies appear to be similar.
When we study the fossil records, a lot of the material is gone and we simply can't find it. And it turns out that asteroids and comets have a lot of materials in common. So even if you do find extraterrestrial material, it's really hard to tell whether it came from an asteroid or from a comet.
And to complicate matters, a comet doesn't even have to impact Earth's surface to ignite a catastrophe. In 1908, a fireball exploded in the atmosphere above the Tunguska Wilderness in Siberia. The heat and energy from the airburst propelled downward like a hot tornado. It propagated across the forest, flattening over 800 square miles of trees. For over a century, some scientists have wondered if the cosmic intruder was a comet or an asteroid.
If it were caused by a comet, you would imagine you'd find in the sediment some record of unusual things like a ratio of helium-3 to helium-4. That could be an indication that it may have been a comet. Another possibility is if you find some strange isotope buried in lakes somewhere. That's tough. This is not easy.
While it's been difficult to substantiate cometary impacts on Earth, physical proof of their colossal power exists on the gas giant planets. And these dramatic events warn that far worse collisions loom in the future, with Earth as the potential bullseye. As we've followed the trail of comets through space, we've passed through the chilliest and warmest places in our solar system. We've also investigated whether these icy bodies have been deliverers and destroyers of life. And new observations prove many of these ancient bodies haven't quietly retired to the frigid outer limits of our solar system.
We think there are several possible end states for comets. In one case, they can actually get pulled right into the sun. In other cases, they can actually get scattered by one of the planets and kind of get kicked out, maybe back into the Oort cloud and never seen again. And finally, they can also actually impact a planet.
We now shuttle back to July 1994. We follow a string of 21 comet fragments called Shoemaker-Levy 9 as they're gravitationally pulled toward the gas giant, planet Jupiter.
If we were riding on one of the fragments of Comet Shoemaker-Levy 9, it would have been truly spectacular because we're heading toward Jupiter and this giant planet is looming ever bigger, and then splat, we crash into it and we throw up a whole bunch of material from the insides. It would be really an amazing journey. The plumes of material coming out of Jupiter were superheated gas heated by this collision and also excavated from the interior of Jupiter.
Shoemaker-Levy 9 left impact scars the size of Earth, driving home the scale of violence that comets can produce if they slam into our planet.
If any of those fragments had hit the Earth rather than Jupiter, we'd have been in serious trouble because they're large and they were coming in extremely rapidly. But fortunately, Big Brother Jupiter took all the hits for us and didn't seem to suffer much in the way of damage.
But even with Jupiter acting as a planetary shield, comets still sneak by the gas giants and have close encounters with Earth.
The good news is asteroid impacts are far more likely to occur because asteroids outnumber comets 100 to 1 in near-Earth space. The bad news is if we do find a comet on an Earth-impacting trajectory, we wouldn't realize it till it got inside the orbit of Jupiter when it started throwing off gas and dust.
In the very unlikely event that a comet could get close to the Earth, you would worry about it because they tend to have high average velocities relative to an asteroid, as high as tens of miles a second. So in other words, they would pack a bigger punch.
While the frequency of near-Earth asteroids heightens the risk of impacts, the speed of comets is equally troubling. This sobering fact has prompted viewer Robin W. from Boulder, Colorado to ask the universe, what poses a greater hazard to humans, asteroids or comets?
Robin, that's an important question. The asteroids are more numerous, so there's more of them that could hit us. But we can track their trajectories and maybe do something about one that's going to hit us, deflect it, for example. The comets are more rare, but we have very little warning when they come in. And also, they move much faster than asteroids, so there is more energy impacting Earth. So I would say comets are the most hazardous objects.
NASA is taking the threat of comets seriously. So far, tracking satellites have tagged 84 near-Earth comets, objects with orbits that come within 28 million miles of Earth's path around the Sun.
There are no periodic comets that currently have Earth's name written on them. But Jupiter and the other giant planets occasionally perturb the orbits of comets, so there could be a periodic comet in the future that will collide with Earth.
Since the beginning of recorded history, over 4,200 comets have been observed, a mere fraction of the total number of these icy bodies. This means billions of unknown comets still lie in wait in the outer reaches of space. One day, a doomsday comet could be nudged out and sent on a collision course with Earth.
If we're on that cosmic highway and it's getting into our on-ramp, we need to worry about it. And we need to worry about it with very little lead time.
There's very little we can do other than sending a giant bomb toward them and trying to deflect them. But that's very difficult when there's only a few months' warning.
Just as comets have inspired awe and fear among our ancestors, they remain a force to reckon with. By continuing to track their tails of dust, we may uncover more clues about these frozen artifacts of our ancient past.
It's pretty remarkable if you think about it. Just a few hundred years ago, we had no idea what they were, we had no idea what they meant. And now we've actually been to the surfaces of comets. We've seen up close and personal what they're really like and what they're made out of. So these mysterious objects have meant a lot to humans throughout our history. They've been agents of change. They've been agents of destruction sometimes. They've maybe been agents of creation.